Office. On behalf of the Canadian HIV Vaccine Initiative Research and Development Alliance Coordinating Office, the ACO, I'd like to welcome you to our webinar on cluster randomized trials, a gentle introduction. For those of you who are new to the Alliance or the Alliance VC, I'll give you a little background. The CHVI Research and Development Alliance Coordinating Office was established by the Government of Canada and the Bill and Melinda Gates Foundation November 2011 at the International Centre for Infectious Diseases, a not-for-profit, non-governmental organization based in Winnipeg. One of the priorities of the ACO has been the development of a new and early career investigators program to advance HIV vaccine research and development efforts. The ACO has put together an advisory group of new and early career investigators at various stages of their careers from across Canada to assist and provide feedback on the development of the program. And with the involvement of our advisory group, we've identified priority topics for the training program, and I am very excited to bring you our fourth webinar in this series. This webinar will be recorded and will be provided to other members of the CHVI Research and Development Alliance via the Alliance VC, or the virtual community. The fall series we are currently preparing for will include a webinar on mucosal immunology, a year in review, and a multidisciplinary research in bringing the social and basic sciences together. This webinar will be of particular interest to students in postdoctoral and junior faculty level, new and early career investigators, as well as principal investigators involved in CRT with an interest in HIV vaccine research. But of course, all are welcome, and I hope you enjoyed today's webinar. The objectives of the webinar today are to describe a cluster randomized trial, or CRT, understand why CRT are conducted, understand how to design CRT, including sample size and randomizations, and understand how to analyze these trials. There will be an opportunity at the end to ask questions during your Q&A period. You may submit your questions also using your microphone if you've enabled it with the system, or you can use the chat box to ask your questions. So without further ado, it's my pleasure to introduce you to Dr. Larry Moulton. He is a biostatistician at the Johns Hopkins University, working primarily on infectious diseases around the world. Vaccine, HIV, tuberculosis, and vitamin A are major interests. Dr. Moulton did his MSc at the University of Texas School of Public Health and Biometry, and his PhD at Johns Hopkins University in statistics. Dr. Moulton is a professor in the Department of International Health and has a joint appointment in the Department of Biostatistics. He is also co-director of the Institute for Vaccine Safety at the Johns Hopkins University. In 2010, he received the American Public Health Association Statistics Section Award for Academia. He has published more than 160 articles, reports, and 3 books.
Thanks to the Alliance for having me here. I will be giving what I call a gentle introduction, but that doesn't mean it will be long and detailed. It means it will be short and sweet. So we may go over a few of these slides a bit too quickly, but I'm counting on all of you on taking some time after the presentation, maybe later this week, to review the slides at your leisure. Now I'll go on here to get the, well, you've just heard of the different things you'll be able to do by the end, but I'll go on to the outline. And we will start off. I see one of the people wanted to know before today's session, what is a cluster randomized trial? And in fact, that's what we'll talk a little bit about, and what are its features. We'll go into the why of it. Why would you ever want to do one of these things? Talk about how to design, and then how to analyze the trials, and then some complications that you can run into in doing so. So we'll start right in here. It's a pretty simple definition, but sometimes it can be the simplest ones that are the most complicated in the end. A cluster randomized trial is just that. It's where there's a group level of people at which the randomization occurs. Most of you, I think, have been involved in one way or another in an individually randomized trials, in which basically it's not this simple, but you're flipping a coin for every person that walks in the door to determine whether they're going to get a treatment or a control. But in this situation, it's whole groups at a time that are being randomized together. And so let me get rid of this little screen here. I can't quite see the whole slide. We've got a poll there going on. Are we waiting for that poll to end? There we go. Okay, so this, once again, we have clusters that are being allocated to either treatment or control. Those clusters can be geographically defined. They might be, say, sub-districts within a district, or they may be defined by characteristics of a community. That is, you might be randomizing all the patients in a pediatric practice, and they may be geographically disparate and interwoven with other folks from other practices, but you'd be randomizing a whole practice's set of children at once, and they would all go together to the same treatment or control condition, and that would constitute a community or cluster randomized trial, of which we have several other names, group randomized trials, community, and so forth. So we'll start off with the first poll here. This is a check all that apply type thing, and trying to figure out which of these is a cluster randomized trial, and take your time there and see which ones you think might be a cluster randomized trial, which ones not. We have most of the folks here now. Is that everyone? If we could go back to the slides then, we've got a bare majority or plurality for the first one. And in fact, that is the most correct answer. And that's that where you have a situation where you allocate villages, a whole village, to using bed nets or not for reducing malaria incidents. In this situation, which has been done many times actually, several different trials, the idea was that everyone in the village would get the bed net, and there'd be an extra add-on reduction in transmission by the fact that everyone is all receiving the bed nets and the mosquitoes don't have anyone to go to. The second one, it's like a group randomized trial in that there is correlated data, but it's basically a situation of whether the infants are individually randomized, and that's the usual situation for a trial such as that. And there's correlated data within a person, but we don't really think of a person as a group, so generally we don't call those group randomized trials. For C, it's a study where you have groups of people that are geographically defined, but it's an observational study. You can't randomize the cities to different latitudes. There they are where they are, and so there's no randomization going on, so they're not a cluster randomized trial. And D is an individually randomized trial that happens at many different places. Within each site, you would have some people on treatment, some getting control or placebo. And so it's not a whole site that would be going into one treatment condition. So really here it's just A. I said it's this definition sounds easy, but it's not always easy to implement.
Dr. Moulton, it's Tanya speaking. We've had a number of participants asking you to speak up just a little bit, please.
Okay, let me bend my my microphone here a bit and see if it can get a little bit louder there. And I'll try and speak louder as well.
Okay, thank you very much.
Okay, you must be oh yeah, you have a way to do that up there. Okay, we'll start off with some basic terminology, because sooner or later you'll see these terms either today or other times when you're talking with people about cluster randomized trials. The first book on cluster or group randomized trials used the term condition a lot, and so we still use that quite a bit. It just means whether you're in the treatment group or a control group, or maybe there might have 4 different arms of a trial, so it's the same thing as different arm of a trial. There's a unit of assignment, which is really the unit of randomization. That's what's defining these trials, which is all at the cluster level, of course. There's inter-class correlation, which is probably the most commonly used measure of how much different units or groups of people are varying. And there are a variety of mathematical definitions of it, but it's the basic idea is that how much the total variance of a situation is due to that occurring naturally between the different clusters. Now, we have a few more like that, a few more parameters we had to think about. The coefficient of variation is very much like that interclass correlation, and it tells you how much the mean values of each group for whatever outcome you're talking about, how much they vary across the groups, and it's scaled by the mean value of all the groups together. And then there's the design effect, which many people from the survey sampling literature are aware of. It really tells you how much more you have to inflate your sample size to account for the fact that there's positive correlation in your data. And so in a cluster randomized trial, you might have to have a trial that examines or gets responses from twice as many people as in an individually randomized trial, and that would mean that you have a design effect of 2. It's the same thing as the ratio of the two variances, whether you're accounting for correlation or not. But the idea is that this is an inflation factor that has to be applied to account for the fact that you're randomizing by groups. And you can use any one of these 3 parameters, ICC, CV, or design effect, to calculate the sample size for a cluster randomized trial. It just depends on what data you have available at the time you're doing your planning. Okay, how is the sound now? Can you hear me a little bit better? I tried to place that mic a little closer. Okay. All right, so why would we use a cluster randomized design? Well, it's like anything else in life. You do things for one of 2 reasons. You either have to or you want to. Okay, good. Some people are saying the sound is better. Well, the times when you have to do it is probably the majority of situations. It's especially when the intervention itself can only be applied at a group level. If you have a media campaign with radio or television advertisements, that's necessarily going to go over a whole part of a city, or even a district. Sometimes you can only apply an intervention might be at, as in health system strengthening, maybe at the level of a hospital to try and get everyone to comply with certain measures. There are logistical constraints sometimes. You might not be able to do the randomization individually. You have political considerations. Sometimes you don't want to be in a situation where maybe people in one part of a town are getting one intervention, the people right next to them aren't, and there's some jealousy or whatever. That can happen. Also, sometimes you might have an intervention. Suppose you have an individually applied educational intervention. Well, you may be going into a household and delivering your educational intervention, and then the next day the people in that household might just talk to their neighbors and basically give them all the information. That would be essentially contaminating them and making controls like the intervention group. And so if you randomize at very much larger geographic areas, that will help to minimize the contamination like that. Well, sometimes we want to randomize these trials to capture different parameters or different effects. I think many of you have heard of herd effects or herd immunity, also known as indirect effects. The Brits call them knock-on effects. It's the extra bang for the buck you get out of applying a treatment to a bunch of people, so that in the case of infectious diseases, if you can vaccinate against the disease, then you can, in some people in a community, then you will reduce the overall rate, the incidence rate, because you'll end up reducing secondary and tertiary, et cetera, transmissions. So you may have these other effects beyond the direct effect of immunizing one person. It reduce their transmission to another. Also, when you get a bunch of people involved in one program, they talk amongst each other, they communicate things, they translate things into their own terms. You can have a very different effect of a program at a group or social level than you do on an individual level. And so you can often get a better idea of what the eventual program effectiveness will be if you implement a program at the level of an entire community. Now here is a very complicated slide, and after the end of the talk here, I'm counting on you all to go into a quiet room and look at it for about 10 minutes. It's because it gets at some of the basic parameters we can estimate in a cluster randomized trial, especially ones that we can't do in an individually randomized trial. And this particular slide is oriented towards a situation which is, I think, is at the I don't know, primary in many of your minds, the idea of infectious disease vaccine intervention, say an HIV vaccine trial. And it's if you were doing an HIV vaccine trial in randomizing by communities, then in any community that you randomize, there would be people who get the vaccine and people who do not. And we'll assume that getting vaccinated is synonymous with being enrolled here. And so you have a whole mess of, maybe 10 different intervention units like the oval on the left and maybe 10 areas of control on the right. And we have, within each of those, we'll be having incident cases coming up, both among those who've been vaccinated, hopefully not too many, and among those who have not been vaccinated. Now, there's different comparisons you can make of these rates. We'll just talk about the numerators, but basically we're really looking at rates. Most often in vaccine trials that are done at the community level like this, the main parameter that is estimated is this one that's called the total effect of the vaccine. And in this situation, it's the comparing the cases among those who've received the intervention and among the enrolled in the intervention units to those among those enrolled in the control units. That is, everyone who you know is definitely in your trial. They signed informed consent, they got the vaccine, and gives you a combination of both direct and indirect effects. A direct effect, the person you immunize has some protection, but also if you immunize enough people in a community, they'll get some of the indirect effects in that some of their neighbors will not be transmitting or potentially transmitting to them. So there'll be both direct and indirect or herd effects. Now, if you look among the people who are not enrolled in the trial, and we look at the incidence in the intervention units among those who did not get the vaccine to the incidence in the control units, those who didn't get the vaccine, well, again, if you've got an effective vaccine and a high enough proportion of people have been immunized, you'll have less risk to those people in the intervention units just because there won't be as much circulating transmission there. And that's the indirect effect you're measuring. The third one, the overall effect, measures the entire incidence in the whole intervention units and everyone in all the control units. And that's a function of the direct effect, the indirect effect, plus the degree to which you've rolled out this intervention. That is, the coverage of the intervention in the intervention units. In some studies, you might only be able to enroll 10% of a population. Others, you'll enroll 90. And this overall effect includes that coverage as well. Then finally, in a group randomized trial, you can measure the direct effect, that is the direct effect of the individual, pretty well just by looking within the intervention units and comparing those who got the vaccine to those who didn't. But this is potentially biased because you haven't done that randomization. People are self-selecting into these trials. You may have approached them, but not all of them are going to sign up. And so this is potentially biased. It's no longer randomized, and so it's something you wouldn't try and do in a community randomized trial. So that was a long slide. We better move on to these others with some examples. These are ones I've been involved with one or another. I came into the middle of a large sexually transmitted disease intervention project in the Rakai area in Uganda. There they had 10 geographically defined units, so it was randomized 5 versus 5. And the intervention, though, is at the individual level. Basically, people taking a few pills, and just like you get a vaccine. But the idea is that it was held. It went on long enough so that the idea was they would capture the effect of HIV attack rate reduction due to secondary transmissions. That was the desire. Unfortunately, it didn't have a lot of effect. So not everything is a clear winner. There's the Lombok Hib vaccine study. That one was quite exciting. We had 800 communities randomized, over 818. Huge study. This one is mainly done for logistical ease. It would been very difficult in this particular situation on Lombok Island to individually enroll 50,000 kids and make sure that they each got their series of vaccines, the same one, because they had to get a whole vaccine series, separated by a month each. And it was a lot easier to basically randomize these hamlets, which are little catchment areas, and they just know that they would just distribute the right kind of vaccine to those communities at that level, and that helped to ensure everyone got the right treatment. So that was a logistical consideration. With Richard Hayes, I was running the biostatistics core for the CREATE consortium. This is funded by the Bill and Melinda Gates Foundation. It's just ending up now. There's 3 different trials in it. They're all community randomized in one way or another. The Zamstar one had a sample size of 24 areas, but it's actually tens and tens of thousands of people involved in the study. That was a factorial design. They actually had 4 different interventions distributed among the 24 randomized areas. And there's a TRIO study. We'll talk later in today about a stepped wedge design. And this was a health services intervention that mainly because of logistical reasons, we could only train a couple of clinics worth of personnel at a time, so it had to be staged. And political reasons, to make sure that everyone got the intervention by the end, we did a stepped wedge design. And then the third of this trio, they were randomizing whole communities, whole areas of hospitals and mine shafts in South Africa to more intensive prophylaxis with isoniazid or just giving it to people with high risks only. So those are a few of the different things situations that call for group randomized trials. I'll go right on here to the correlation, which is a big problem in all of these studies, which is that we always have it, and it's almost always positive correlation. Correlation within people in a community, it happens because of variation between communities. It's 2 sides of the same coin. The between cluster variability will engender within cluster correlation, or you can think of within cluster correlation causing between cluster variability. It's the same thing, and it's almost always positive. The reason it's a problem is that we don't account for it, we'll have increased variance estimates. They'll be bigger than they really than we would have had if we. They'll be bigger than we would have had an individually randomized trial, and if we don't account for them, then we'll think we have more information than we really do. This picture is just to give an example of that between country variability, in this case, making within country correlation. So if you picked one person out at random and it turned out to be someone in France, and then you looked at the person who lives in the house next to them, if the first person is speaking French, that tells you some information about the person in the house next to them. Is that because of the within-country correlation, knowing that the first person you picked randomly speaking French tells you that the person next to them is likely to do so as well. So the idea is that it really can give you more information than you would have if you just picked someone else completely at random from all of Europe here. You wouldn't have any idea of which languages they're speaking. You won't dwell on this slide. That's for your reference later, just to remind you what exactly are the coefficient of variation, the ICC. Basically, these measures are functions of that between cluster variability. In this case, it's called sigma squared b for between. Go right on here. The basic idea is that if the ICC or the coefficient of variation k are large, then you have large variability across clusters, and when they go down to 0, then essentially you're in the situation where it's about much extra variability as you would have in an individually randomized trial, which is none. So we'll take a brief break here for another poll. I don't know how many of you have been subject to telephone surveys. Someone calls your house and they often ask, who's the oldest person in the household or something like that, and that's the only person they want to know about. They just want your opinion. Why is that? Why do they generally just ask for one person's opinion? Okay, well, I think we have a clear winner here. I'm disappointed no one chose the father-son one, but in fact the answer is the second, is that there's high within household correlation for a lot of things. If you ask one person, how did you vote in the last election, their spouse or child might be more likely to say the same thing than a different thing. And so it really is that middle one. Just knowing one gives you most of the information. Now, if you ask for everyone in the household, you will end up with more information, but not a lot more. And so right away you have a diminishing return situations, which we'll have in cluster randomized trials as well. Okay, we'll talk a bit about sample size now. I guess the main thing is to be thinking that we have these diminishing returns. That is, the first few individuals we see in a cluster are giving us more information per person than if you have a lot of individuals in a cluster. And to calculate the sample sizes, you've all done this, I think, in one classroom situation or another for individually randomized trials. You need your standard parameters, your type 1 and type 2 error, the effect measure you're trying to find, the effect that you're trying to find, the variance of your measurements. There's one more measure you need, which is your between cluster variability. And this can be expressed with different formulas. You can use the coefficient of variation, the interclass correlation, or a design effect, which is probably the least useful of all, just because it's specific to a given design. The first two are generally more useful for actually calculating your sample sizes. And here's just a picture from a sample size article that I like, Hayes and Bennett, International Journal of Epidemiology. It has simple sample size formulas for a variety of situations for cluster randomized trials. This was a very particular one in which they had matched pairs of clusters. So it was a highly stratified design where the strata were pairs of clusters of people. And anyway, what they found out, depending on how much the coefficient of variation was, that after the first few hundred people in any community, it didn't really pay to be measuring outcomes on a lot more people. Once you got to a few hundred there, that was it. That got most of the information, and you couldn't really reduce the number of communities needed much more by going on and getting everyone in a community, thousands of them. So again, that's the diminishing returns. So I think we've got a poll here, which take a minute to look at. consider two different ways to implement a media campaign and study it in a bunch of cities. And one of them, you have 20 cities, you randomize 10 versus 10 and interview 100 teens in each. So there's 2,000 kids interviewed altogether. The next one is 10 cities total, 5 versus 5, but more teens per city with a total of 2,500 teens. Which do you think might be better? Yes, it's so these are 100 teens for each of 20 cities at the start. That gives you 2,000 overall, and if you have 250 in each for 10, that gives you 2,500. And so you actually have more teens seen in the second study than the first, but it's not that much more. And generally, cities are so variable for all sorts of reasons. In general, you'd be better going with a smaller sample size in terms of teens and a much larger sample size on the side of the level of the city where you're randomizing at. So almost always the answer would be the first one, randomize to 20 cities. If there were really almost zero correlation within a city among teens, then you might go to the second situation. But in practice, that would be too risky, I think. Almost always there's going to be a lot of differences across cities. Okay, well, let's go to the next slide here. Better move on. Cluster formation. This can take a while. You want to give a lot of time to planning any trial because sometimes you'll, especially with geographically determined clusters, you can draw the lines where you want. You might draw it at around sub-districts or group a couple of village health worker catchment areas or 10 catchment areas. When you got geography, you can draw a line anywhere. And you have a trade-off here. If you make the clusters small, so you can have a lot of clusters, then you'll, with the sample size formulas, you'll have more power or more precision. On the other hand, if the clusters are really small, say 4 or 5 households at a time, it may be that there's so much possibility for contamination that you'll lose power because the intervention will start looking more like the control situation. So there's always this trade-off, and you can't really tell for sure in advance what's going to be best, and that's what makes it sometimes more of an art than a science. And sometimes to estimate that amount of contamination, we have to have focus groups and do research and all sorts of things. One thing you can do when you're doing geographically based randomization is include buffer zones to reduce the contamination between clusters. Here's an example from the Zamstar trial. They actually had 2 buffer areas around their area of measurement, which is the light blue. They intervened in a large area just to make sure everyone in the measurement area actually had a good opportunity for the intervention. So they actually had that had part of the intervention area being a buffer zone where they applied the intervention but didn't measure the results. And then they had the larger buffer area around it, separating it from the next community. So we call that the fried egg design for obvious reasons. This is another trial I was involved in, a big pneumococcal vaccine trial, which we think was the first one that FDA ever approved for potentially being a pivotal trial, which is done in a cluster randomized fashion. As it turned out, an individually randomized trial out on the West Coast beat us to it, so it was not the pivotal trial in the end. But we had these problems of how to actually form those clusters, and we came up with what we thought was a pretty good solution for that. Okay. Now we're just going to take a break and think about why do we use randomization at all in clinical trials. There's several different reasons, and check all that apply. So this is for any kind of clinical trial, cluster randomized or individually randomized. It's the same thing. Okay, well, that looks pretty good. We've got a lot of good answers here, and it looks like you got all the right ones as far as I'm concerned. To avoid bias, to try to get balance, and to help ensure masking. Those really are the main reasons we randomize. Here, we'll go on to the next slide here now. And I've got a list of them, which include the ones we just saw. The big one that I put in bold is not only to avoid bias by the investigator, is to avoid the appearance of bias. So often you have to go an extra step just to make sure that the randomization is clear to everyone and no one thinks anyone's cheating. At the bottom, we see a minority statistical position, which is that that randomization is necessary for any kind of statistical inference, but we do things all the time in observational studies. We calculate our confidence intervals. It really isn't. So you may run into that at some point, but don't worry about it. Okay, well, let's go on here. Probably the reason I'm talking about randomization a little bit here is that usually these cluster randomized trials have small numbers of clusters. Not always. We had that one with over 800. But a lot of these have 10, 15, 20 clusters. With numbers that small, you're really at risk of getting bad outcomes. You can have bad luck. You can't, if you have 5 variables, you can't stratify 10 different units 5 ways. 2 to the 5th. That's a large number of different small strata you could make. And so we've come up with some ways to actually constrain the randomization, and because of time here, I'm going to actually skip over this, but it's just an example here of how even if you really stratify as much as you can, you could still be off by the baseline imbalance of 10% or more. And so the idea is that you can then try other ways, constrain them that we've come up with. Anyway. Well, now I'll mention a few different things you can do with cluster randomized trials. Slight variance in the design. One thing you can do is get a lot of baseline data and adjust for the baseline information. This can let you have fewer clusters, smaller sample size. Of course, you have to trust your baseline data, and often in many situations we find that right at the start of the study we're not as good at getting those kind of data out of a population as we are at the end. But that can increase efficiency. We have crossover designs, which are hard to do with clusters of people. That is, have them start off in one treatment arm and then go to another treatment arm and then later on come back to the first one, or some going one way, some going the other way. It's easiest just to have people in one treatment arm altogether, just like it is for ordinary trials. And then the next slide is an example of variable implementation design. Whoa, here we have this is actually an example of a rotavirus vaccine study that we planned at one time, but we never got the money to pull off. Anyway, the idea was to sort of see at what point the herd effects take off. And so you have some clusters which are like this, C, in which most of the people are vaccinated. You have other ones, clusters where nobody is vaccinated, or where almost everybody is vaccinated. And the idea would be to see, do you start getting more for where you have 90% vaccinated, do you have 95% protection, or maybe it's at the level of 50% vaccinated, you start seeing more than 50% getting protected. But that's just a possibility among many others, of course. All right. I'll talk a little bit about the stepped wedge design. Again, I see time slipping away from me. But this has become more popular in recent years because it's a design in which, by the end of the study, everyone has received the intervention, which is okay if the intervention works. It's no special advantage if the intervention doesn't do much at all, though. But it started off, I think, many years ago at the CDC. They were doing this. They'd phase it in a study one step at a time, and then one geographic area, and try it out, and then go to another geographic area until everyone in the whole region had received the intervention. sometimes people consider this to be, let me get this thing down here, to be ethically superior to a parallel design, which right at the beginning half of the clusters get intervention and half don't. But it can take longer to get the same result. Sometimes it can be shorter, but it could be longer. And it's no more ethical if the intervention, in fact, doesn't work. You can just easily just promise to the population, put it on paper, that at the end, if the study shows that it worked, whatever your intervention is, then you'd just give it to everyone for a year or two. So it's called stepped wedge because as you phase areas in, if you make a little graph of it, it looks like a bunch of steps, and you get a wedge shape at the end. This was a situation that we had in Rio de Janeiro. We, at every step, 2 months, we'd do a training of 2 clinics. So there are actually 2 clinics being phased in. It takes 2 months of training, essentially, and then you go on to the next 2 clinics and phase them in. And eventually, everyone got the intervention. So that's a stepped wedge. It's called one-way crossover as well because you start off in a control condition, one particular clinic, and then eventually that clinic ends up in intervention phase. So everyone is contributing to both control and intervention, except maybe the clinics at the very start and the very end. So here was another example of stepped wedge design. There can be problems, though. You can have a loss of power, especially if there's very little variation across communities. It can be tough to balance the randomized. There can be a problem if you have lag times between when people are exposed to the treatment and when their results are. Now, for some, say, hospital-based studies, it can be very quick, and a stepped wedge might work. You might go into one ward and just, one day give everyone a new kind of gloves that will be better for reducing infections. And then the next day, or the next, probably the next month, you go into the next ward and give everyone there the special gloves. Well, and you see your results right away. You see the infections being reduced, hopefully, right within the first few days, if in fact it had an improvement. But if it's something that takes a long time, which happened with us with tuberculosis, it starts getting very complicated in the analysis, and it causes a lot of headaches anyway. So again, that's the kind of thing you don't want to try at home. I'll give a few references to some review articles, and probably the best one to read if you're actually tempted to do one of these studies is this one right here. It's a pretty fair description of the variety of ways you can do these stepped wedge studies. And they mention all the drawbacks as well. So I'd say that's a good one to do before you actually jump into a stepped wedge design. Okay. Oh boy, I was too late on checking my chat here. Someone was asking me about randomization and blinding. And actually, randomization, I could say it doesn't ensure blinding. You're right, I may have been a little bit strong on that when I said randomization ensures it. It should be help ensure blinding. Randomization can help ensure blinding because it's random, you can't really guess who's getting a treatment or not. So that's a good point. Okay. All right, well, let's go on to the analysis now. This is a very famous quotation by Jerry Cornfield about cluster randomized trials, and we're basically saying that you really have to analyze as you've randomized in terms of the analysis has to account for the cluster level correlation. If you don't, you'll have less information than you think you have, and your confidence intervals will be too narrow. Your statistical significance will be more than you think you have. You're deceiving yourself. We can use a lot of methods we use for other correlated data problems. You can start off with the individual and then account for correlation, or you can just take a mean of every group and just do a basic t-test. It's very simple analyses you can do as well. The idea is to choose one that is robust to your situation and gets almost all the information out, and it doesn't lead you into thinking that you have more information than you really have, because it does account for the correlation. A big problem here can be this business of actually figuring out who to count for the intervention. You have intent to treat definitions, and per protocol definitions are not always clear when you come to randomizing clusters. So you might randomize a whole cluster of people to get the vaccine. It may be that in no one cluster does the whole cluster get it. And so a pure per protocol definition might eliminate the whole cluster, and then you wouldn't have a study left. So everything gets a little bit different when you're talking about these parameters in a cluster randomized trial. So again, depending on how many levels of correlation you have, you might use more fancy models and so forth, have multiple or multi-level random effects models with different random effects for every level. But the basic idea is that you just have to make sure you account for that correlation. You can use the random effects models, generalized estimating equations. There's some methods called quasi-likelihood that let you adjust for that over-dispersion. Or, as I said, that you can do the simple thing. You can just take the mean of every cluster and do your t-test or whatever you want with it. So you have a lot of analysis options. We won't go into those today. But we'll take a quick poll here, which is what happens if you just do an individually randomized type of analysis on a cluster randomized trial. What will happen with the confidence intervals you calculate if you ignore that clustering? Yeah, okay, people are answering right away. Okay, so if you ignore the clustering, what do you get? Well, it turns out you get a situation where you have less information than you think you have, and in terms of a confidence interval, that means the confidence interval you calculate is shorter than it should be. That is, it implies that we have more precision, more knowledge of where the true value is than what we really have. So looks like 3/4 of the people here, 80%, are getting this one right. They're shorter than they should be. And so you get fooled into think you have more information than you really do. There's a lot of types of bias you can have in these studies, especially since sometimes, as I said, you only have small numbers of clusters. 10 clusters, one cluster has a problem, like in one trial we were designing. We were worried a new international airport was going to be built near one of the clusters, and that one was actually only going to be about 8 clusters, and that would have had a big impact on the whole study. Then you have always a problem with people traveling. What happens if it's a long-term intervention? They start off with one cluster, they move to another. Well, that would reduce the magnitude of effect. You have to decide how you're going to deal with them. Do you censor them? Do you add them into the new, or do you keep them in the old intervention? There's all sorts of levels of complication that you get in these studies that you don't have with the individually randomized trials.
Dr. Moulton, it's Tanya speaking.
Very into how.
I just wanted to let you know that we're running out of time. We need to wrapping it up very quickly.
Okay, great. So we have a lot of potential biases, as I mentioned, including the one just from plain bad luck if you didn't have good luck in your randomization. Okay, you have informed consent problems because now you have to think about consenting whole communities in some situations. That's a whole lecture in and of itself. The drawbacks, of course, is that you take a lot larger sample size to get the same answers in an individually randomized trial. And you have a lot of inferential problems. We've had people who were randomized, not enrolled, but even enrolled, but not randomized because they came from outside the whole study area. These things don't happen in individually randomized trials. So these are harder to pull off. They take larger samples, harder to analyze. but you can estimate things that you can't estimate otherwise. And so if you really want to estimate those parameters, just make sure you have a lot of time and money. I guess that's the biggest takeaway. Always get more time and more money to carry these out. Further reading, we got a book just came out last year there for health services. Of course, our book isn't too bad. We'll revise it someday. It's a good soporific. 4 pages per night will put you to sleep, but it's pretty easy to follow. So I think we better open it up for the last 5 minutes here for questions. Thanks for sticking with me to the end, and I hope you can review the slides later on.
That's terrific. Thanks so much, Dr. Moulton. I just wanted to review for the participants that are on the line that you can raise your hand using the top menu bar. There's a individual there with a hand raised. You can use that to raise your hand if you have a question. Also, you can use the chat box. We've had a couple come in during the registration and during the webinar. So I'll start with those and let you guys form some questions if you have any. One that came in during the registration, Dr. Moulton, is what are the limitations of cluster randomization trials?
Well, the main limitation is I would say that takes a lot more people often to pull off, and so you may not have enough experimental material. You may not have enough communities to be working with, and I've seen some studies abandoned at the planning stage because they said, well, we only have 8 communities, and they did sample size calculations, and they found to find an important effect, they just couldn't do it, and they'd rather instead of spending $1 million to get a null trial, they just had to abandon the idea. They just couldn't get enough clusters. So that's a big problem right there.
Okay, thank you. Another question that has come in via chat is from Robert Reinhardt. He asks, could you reflect on any significant ethical considerations in randomization in the communities or obtaining consent? For example, a trial might further look at using HIV therapy in communities to reduce community viral load and examine treatment as prevention. Ethical considerations there?
Okay. Well, if the intervention is applied at the individual level, okay, and so you're treating individuals in general, you're on better ground than in situations where you're randomizing an intervention that's necessarily applied to everyone, say some new additive in the water supply or something like that, treating people through the water supply. The problem with the treatment as prevention, there you have the same problem you would have as in an individual randomized trial. It's not really a cluster-specific one, which is that you're randomizing treatment or not. And so that consideration would be the same for individuals and groups. So I think in those TAP type of designs, the ethical concern is more the ones you worry about at the individual level, because of there's really not going to be in general harm or potential changes in the outcomes of a lot of people who aren't enrolled in the trial, except maybe a reduction in transmission, which you're trying to get. I'm not sure I've answered that, but I think in this case that is not much beyond the special considerations you have for individuals.
Thank you very much.
You don't have to get really
terrific.
Permission from a whole community.
Okay, I just wanted to point out to the participants on the line, there is an evaluation available, and we hope that you'll go there and follow that link and do the evaluation. It's important for us to get your feedback and help us to enhance and improve our webinars. So go ahead and do that. And if there's any we have 1 minute left if you have any other questions you'd like to ask. There's one coming in from Jamie Weaver.
Good question. Can they download the slides?
We will be making we'll have to talk to Dr. Moulton about that offline. We can certainly, the archive webinar will be available on the virtual community, and we'll, if there's any, we'll let you know as soon as we've had a chance to talk to Dr. Moulton about whether that's possible. There's another question here from Susan Yelmy. Is there preliminary evidence that the intervention is likely to be beneficial from observational studies?
Well, you may be talking about a particular one. I don't know if that was about the TASP or something else, but in fact, usually we have a lot of observational studies before we embark on a very large, expensive community randomized trials. Just because these cluster randomized trials cost so long and they go so long, we want to make sure that we have a good evidence to start off with. One example would be the male circumcision trials that took place in Africa. We had a lot of observational studies, but none of them were fully satisfactory. But once we had accumulated a lot of information, then we pulled off 3 different randomized trials. Those were individually randomized trials, but the same idea is that it was a very expensive type of intervention to do or study, so you want a lot of observational data first.
Okay, thank you. It's now the top of the hour wherever you are, and it's time for us to sign off. Before we do, though, I'd like to take the opportunity to thank you, Dr. Moulton, for sharing your expertise with the members of the CHVI Alliance virtual community and our new and early career investigators and all of our attendees, all our participants from Canada and the U.S., Kenya, Nigeria, Uganda, and South Africa. I also wanted to thank our practicum student, Dr. Julie Lajoie, who was integral in the planning of the webinar, as well as the advice from our new and early career investigator advisory group. And lastly, to thank Elizabeth Hanless, our instructional designer, who has been facilitating this webinar. So thank you very much. If you haven't had a chance already to complete the evaluation, please take a moment to do that. It doesn't take that long. And we will be posting the archived recorded version of the webinar on the virtual community, and we'll let you know via the news forums once that's available. Thank you very, very much. We really appreciated your presentation, Dr. Moulton, and taking the time to work with us. It's been a pleasure.
Okay, well,
okay, have a great day, everyone.